Hi, my name is Liren, and I'm a PhD student at the research group led by Dr. Marija Popović at the University of Bonn. Today, I will introduce our new work, Adaptive Resolution Filter Mapping using Gaussian process fusion with integral kernels. Filter mapping is crucial for helping us understand many natural processes, especially in agriculture scenarios, such as temperature, moisture, or wind densities, are crucial information to help farmers make decisions. However, these phenomena usually show complex spatial variations, which are hard to capture by using static sensor networks. Recently, unmanned aerial vehicles become flexible and cost-efficient alternative for data acquisition in a wide range of applications. Different from manually control the UAV for data collection only, we aim at exploiting the autonomy of these platforms, so that the UAV can monitor the fields in an autonomous and targeted way, such as gather information from regions of interests. Following this idea, we use new sensor data to update our map and replan UAV paths based on current map state, in order to maximize overall information gain given limited operation time. In this work, we develop an online mapping strategy that can cater for such robotic applications. However, developing mapping approach for field monitoring in an online environment is non-trivial. The challenges come from two aspects. First, as the nature phenomena usually show heterogeneous distribution on the field, our mapping resources should be allocated adaptively in order to achieve a compact map representation. Our key idea is to only map regions of interest at a high resolution, so the details of these areas can be maintained as accurately as possible. Besides, spatial correlation often characterize our mapping objects. Ignoring such key element will limit our mapping quality, especially when the sensor data is sparse and noisy. Second, using off-the-shelf UAVs also poses limitation on onboard resources, such as computing power and battery life. In order to efficiently replan the path based on current map state, the map must be compact, easy to interpret, and accurate. We propose to use Gaussian process fusion to do field mapping. Gaussian process fusion exploits a trained Gaussian process model to initialize a spatially correlated grid map, which serves as a prior map for recursive updates. During mapping, sensor data are assumed to be noisy observations of corresponding grid cell. We then calculate our posterior map state using Bayesian fusion. As no measurement history needs to be preserved, the notorious time complexity of Gaussian process regression can be alleviated. As our major motivation is to generate a compact map representation, we need to adjust the map resolution in a targeted way. For this, we save our map with ND tree structure and merge uninteresting grid cells during mapping to compress the map. For adapting map resolution, we need to modify only the map mean and covariance. However, this operation requires the posterior map state at new mapping positions, which cannot be efficiently acquired when the map state is only maintained in a point-wise manner, such as at center point of grid cells. To address this problem, our major contribution is to use integral kernel to bridge the gap between adaptive resolution map and Bayesian fusion. In our map representation, each grid cell represents the average function value over the area it covers. Different from kernel function defining the spatial correlation between points in the space, we define the underlying Gaussian process model by integrating the mean and kernel function over grid cells in our map. Therefore, we naturally encode the mean and correlations of parent nodes in their children nodes. This allows us to summarize the children posterior into their parent by a simple linear transformation of multivariate Gaussian distribution. In our mapping approach, we initialize our map to the highest resolution and monotonically reduce the total number of grid cells by merging operation, which facilitates online mapping efficiency, while maintaining spatial correlations of the map in a theoretically sound fashion. We first compare our mapping approach with several baselines using long-mover flight pattern to exclude the impact of planning. The baseline approaches using cell independence assumption, showing B and C, fail to provide accurate maps. The baseline DEF, considering spatial correlations, can reflect the underlying smooth structure and provide more accurate mapping results. However, they are not efficient in terms of map update or memory consumption. For example, our approach achieved 2 times faster map update and only consumed 10% memory compared to our major baseline F, which is a fixed resolution version of Gaussian process fusion. Our approach strikes a good balance between mapping quality and efficiency. We also provide an offline reconstruction based on our online mapping results, which clearly indicates the strength of our approach. Namely, during online mapping, we adapt the map resolution to facilitate online performance. Since our map is still Gaussian processing in a sense, we can recover our map to any desired resolution in post-processing, which could then be used as prior map for future monitoring tasks. The lab picture shows our mapping results of temperature distribution on a field near Bonn, Germany. The details of region of interests, which are high temperature areas shown in red color, can be accurately retained. This indicates that our mapping approach is able to compress the map in a targeted manner. We also integrate our mapping approach in informative path planning framework, where the goal is to efficiently reconstruct information on region of interest in an online environment by actively replanning the flight path during mission. The plots show that informative path planning using our mapping approach can achieve low mapping error and high coverage of regions of interest with the shortest average mission time. To summarize our work, we propose to use Gaussian process fusion for online field mapping. In order to handle resolution change, we introduced no usage of integral kernel. Our mapping experiments show the efficiency and accuracy of mapping approach compared to several baselines. Furthermore, by integrating our mapping method in informative path planning framework, we show a better performance of finding region of interest in online environments given limited operation time.